Sam van Damme. I'm a PhD researcher at Ghent University and IMEC. And in this presentation, I will show you the content of a paper, clustering-based psychometric no-reference quality model for point cloud video. In the 1977 Star Wars movie, Episode 4, A New Hope, there is this iconic scene of Princess Leia sending a message by means of hologram. Now, of course, back in these days, this was still completely science fiction, while now in the 21st century, this is becoming more and more realistic. For example, in this German circus that is using holograms instead of real animals to show its acts. Now, of course, these hologram applications or point clouds, which is what we are focusing on, are local applications. If we want to send these over a network, such as Leia was doing it, we are in bandwidth requirements in the order of gigabits per second, which is simply infeasible. So we need compression. Now, of course, when we say compression, we also say that we are actually affecting the rendering quality of the point clouds and thus the end user experience and perception. Of course, we want to monitor and maximize this. And the most straightforward way to do this is by means of subjective evaluations. But these are, of course, expensive, both in terms of time and money. And also, they don't allow for real-time monitoring and evaluation of the quality of the system. As such, there is a need for objective real-time quality of experience monitoring. This brings a couple of challenges. First of all, we want a modeling that is near real time, such that, for example, for an adaptive streaming scheme, we can adapt the quality and optimize the quality near real time. And for this, of course, we need objective metrics that are computationally friendly, and then we are most often looking at non-reference metrics. Second, we of course want a high correlation to subjective perception, as the end user experience is what we want to maximize in the end. And in order to be able to train and evaluate the system without human intervention, we make use of a highly accurate objective benchmark with a high correlation to subjective perception, which is often a full reference one. And then, of course, we also need a model to relate the non-reference metrics from the first challenge to this full reference benchmark. And then third, as we want a system that can easily adapt to new types of content, whenever a new video, for example, enters the server or the database, it could be interesting to cluster similar video sequences together and to build a model for each type of video. Now, how did we do this? We built the following methodology. So imagine that we have a certain amount of point clouds, which we embed in a video, and then send this video over a network. Then, of course, this video can get impaired. Then at the client side, we calculate a set of objective non-reference metrics, which we then use as an input to a KNN classifier. This classifier then outputs a certain class C together with a set of weights WC0 to WCN, which we use to take a linear weighted combination of the set of non-reference metrics. After this, we input this in a sigmoidal mapping function with two parameters AC and BC, which we base upon the psychometric curve fitting proposed by Fiedler et al. This then, in the end, outputs a certain quality Q, which of course resembles the subjective perception of the user. Now, at server side, to train and evaluate this, we can, of course, use the reference video. And together with the impaired video, this offers a possibility to calculate a full reference metric or full reference benchmark, which we chose to be VMAF based on the high correlations for point clouds with subjective scores we saw in our previous work. We can input this full reference benchmark both to the linear regressor and to the sigmoidal mapping to optimize the weights and the parameters. And of course, also to evaluate the output value Q in terms of Pearson linear correlation and root mean square error. Now, for the KNN clustering mechanism, of course, at training, we need to predefine the number of clusters. And we have done this by maximizing the so-called silhouette score, which is a metric that calculates the trade-off between how close all elements in one cluster are together and what the distance between the separate clusters is. In our work, this turned out to be maximized with a value of 4 clusters on a data set I will discuss later in this presentation. Second, the psychometric curve fitting, as said, is a sigmoidal mapping of a linear combination of non-reference metrics, which is based on the QoS-QE relationship by Fiedler et al., of which we train the weights and the parameters for each cluster by minimizing the mean square error with VMAF. Then in terms of metrics, we used 7 non-reference metrics, being bandwidth, blur and blur ratio, noise and noise ratio, blockiness and spatial information, which can all be calculated on a frame level. And as said, we used VMAF as a benchmark based on the correlations to subjective scores in our previous work. Now, to evaluate this, we built a data set based on 4 point cloud objects from the 8i dataset we extracted. And we used these to create 16 source videos between 18 and 50 seconds of length. We did this by creating multiple setups of the figures, placing them in a circle, a line, a semicircle, or a square, and also by combining different camera movements, being rotation, zoom, pan, and zigzag. Then we use these source videos to encode them using the VPCC encoder, using 5 port representations between 2.4 megabits per second and 53.5 megabits per second, and using 2 resolutions, 800 by 592, and also the full high definition. The frame rate we fixed at 30 frames per second. Furthermore, we also emulated a dynamic adaptive streaming over HTTP or DASH protocol with bandwidths between 15 to 140 megabits per second, and also an infinite megabits per second, which of course means that the video is not affected by the streaming. We also used 5 different buffer lengths from 0 to 4 seconds and 3 allocation algorithms, being greedy, hybrid, and uniform. All of this in the end resulted in 453 sequences in total. And this brings me to the results. Here you can see a table which shows the Pearson linear correlation and root mean squared error of the output of our model to VMAF after cross-validating on the different videos, where each time we took all sequences of one particular source video as a test fault and the other videos as a training fault. Note that the only exception to this methodology is video 10, because this is isolated in his cluster. There we just did a 5-fold cross-validation on the different configurations of video 10 itself. Now, looking at the results, it is worth noticing that we are obtaining rather high correlations of about 0.99, except for the cluster 3, so video 10, in which we are only obtaining 0.84. One explanation for this behavior is, of course, the limited amount of data. Because we are cross-validating within one particular video, then during training, not all possible configurations of the video seen. Another possible explanation, of course, is that video 10 simply can be an outlier within this complete data set, which is possible, as we have seen at this showing higher values of blur and blur ratio when compared to the other videos. Second, something I would also like to highlight is the larger root mean square error of cluster 2 compared to the other clusters, while still maintaining a high Pearson linear correlation. This is due to the constant either over or under prediction in cluster 3, depending on which fold you are looking at, which is also shown from the figure over here. We expect that additional data to obtain a more coherent cluster or even an improved clustering mechanism could further solve this issue. If we then have a look at the average PLCCs and RMSEs averaged over all the clusters and then compared to the cases without either clustering or sigmoidal mapping, we see that both in terms of correlation and in terms of root mean squared error, the combination of both is outperforming the other cases. Especially for the clustering mechanism, we see an improvement from about 0.11 correlation value, and also a decrease in RMSE of 0.02, so which is limited for the linear regression only, but 0.12 when combined with the sigmoidal mapping. The sigmoidal mapping, when compared to the case without, is also showing marginal gains in terms of Pearson linear correlation of about 0.03 to 0.04, and also a 0.03 gain in RMSE. Note that this is only the case when combined with the clustering mechanism, because without the clustering, it's even getting worse, which is interesting to see. This brings me to the conclusions of this presentation. So let me couple this back to the challenges we predefined earlier. As stated, we needed an objective, computationally friendly, non-reference metric for ensuring the real timeliness, which we addressed by creating a model consisting of 7 state-of-the-art non-reference metrics. Second, we required a high correlation to subjective perception and, of course, also to an objective full reference benchmark, which was FEMAF in this case. And we had results of Pearson linear correlations up to almost 0.98 and RMSEs below 0.08. Furthermore, we also defined that we would like to cluster similar video sequences together for easy adaptation to new content types, which we realized by implementing a KM clustering mechanism. In terms of future work, it is so that we characterized the videos on a rather large part of the video, so also within the light of real timeliness. It would be interesting to see whether we can also realize this more on a per GOP or even per frame level. And second, currently we limited the types of distortion to VPCC distortions. It could be interesting to see whether we could further investigate other types of distortion, such as GPCC. This brings me to the end of this presentation. Thank you very much for your attention. And of course, if there are any further questions, please don't hesitate to contact me on the email address as shown on the screen. Thank you very much.